the next possibility in a single phase full wave rectifier, the load can be the RL load. The meaning is that you have a resistor and inductor which are in series connected and they form the load. This is known as the load. Now again, since it is the full wave rectifier, we will have all the 4 diodes in the circuit, and the load current now will reach a periodic steady state condition after startup transients. Since the inductor is present in the network, the inductor will create sudden startup transient because inductor do not allow a sudden change in the current. The full wave rectified sinusoidal voltage across the load, if we can talk this V0, then it can be expressed as the Fourier series, which is the combination of a DC term and even harmonics. So the voltage V0 we can have as a function of time t. This is the DC component V0 plus certain harmonics are present in the system, which is given by the Fourier series expansion. So Fourier series expansion, we have Vn cos of n omega naught t plus pi, where this n is basically the degree of harmonics or the order of the harmonics. And since it is even harmonics, we have 2, 4, 6 and so on till infinity. The DC voltage V0 is basically 2 Vm by pi that we have seen earlier also. And the Vn can be given as 2 Vm by pi, and this is the multiplication factor depending upon what the order of harmonics we have. So 1 by n minus 1 minus 1 by n plus 1. Let us see the waveform. So this is the voltage current waveform. If we see the output voltage and the output current, so for both the positive waveform and the negative waveform of the input supply voltage, we have the circuit which give a rectified output voltage and the output current. The diode D1 and D2 will be on in one half cycle, and D3 and D4 will be on in another half cycle. So here you have D1, D2 on, and here you have D3, D4 on. The voltage and the current of the source, which will be Vs and Is, will be impacted because of the presence of the inductance. Now, if the inductance is large and the current is nearly constant, then in that case, you can see the voltage and the current. Here, sudden dip was seen in the current, but it will be pure square waveform that we can see for the current. So, the disturbance that is present in the current due to the transients will not be there if the inductance value is very large. Also, the output voltage and the diode current also will not be getting impacted when the inductance value is large. The current which is flowing in the RL load, that is I0, is computed using the principle of superposition. Each frequency is considered separately and the results are then we combine, because you will have certain degree of harmonics which is present in the system. The DC current and the DC amplitude, if you see the current I0, we can easily find as V0 by R, which is the current which is flowing in the resistance. But the harmonics In, because this is the frequency component with the order n, can be found out by Vn by Zn, where Zn is basically the impedance which is found out by R plus j omega L multiplied with the order of the harmonics. Now, if the omega value is very more than R, this is what we say that the inductance value is quite large. The load inductance may be relatively large or may be made large by adding some external inductance. In that case, what we can say that the current I is basically equal to approximately the average current. And this average current is again V0 by R, which is equal to 2 Vm by pi R. So we can neglect this harmonics component when the inductance value is quite large. The RMS current is also approximately equal to the average current because you don't have any AC component present in the circuit. What do we talk about the harmonics with order n? If the harmonics increases, then the voltage decreases. And for an RL load, with the increase in the harmonics order, the impedance will increase Zn, and the combination of these two factors, that is the decrease in the voltage and the increase in the impedance will result in the decrease in the current rapidly with respect to the increase in the harmonic order. So greater the harmonic order, the lesser the current which is flowing in the system. The significance in the RL load, we have the DC term as well as the few AC terms which are usually necessary to describe the current in the RL load. So we have seen this current expression, it will have the DC term as well as the term which is resulting because of the presence of harmonics. So this is occurring due to the inductor present in the load. Now, if the load is made up of RLE, means you have the component R and L, and together you have certain DC source which is also present as a part of the load. Here application, if we talk about this RLE load applications, may be in the DC motor drive circuit or in the battery charger. So these are famous example of the RLE load where you have the DC motor drive circuit we can see, or the battery charger circuit we can see. There we can comprise this RLE together to present a load. The mode of operation for this type of network can be in the form of a continuous current mode or in the form of a discontinuous current mode. And the DC average component of the current which is flowing in the circuit, on applying the Ohm's law, we can say that V0 minus VDC by R, where V0 is the voltage across this RL component, so it will be V0, and VDC is the voltage in the DC source. So V0 minus VDC by R, you will be getting the total current. This V0 we can again substitute as 2Vm by pi, and we can modify this equation as 2Vm by pi minus VDC by R. So the waveform for the continuous current mode and the discontinuous current mode, we can see it. Continuous current mode, the circuit is energized and the load current reaches the steady state after a very few periods. Whereas in the discontinuous mode, the load current returns to zero during every period. So you cannot have the load current zero here, but you will be having in the discontinuous mode, load current will be zero. So continuous current mode, load current is always positive. You can see that the current is always positive for the steady state operation. And there is one pair of diode is always conducting. The voltage across the load is a full wave rectified sine wave. So when we say that the voltage V0 for both the half cycle, you have the rectified signal, and only modification to the RL load analysis is in the DC term of the Fourier series. So in the continuous current mode, you will be having the current which is positive, and in the discontinuous mode, if you see, the load current is returning to zero during every period. So the current, if you observe the waveform, it is returning to zero, then it is charging, and again it will be discharging and reaches to zero. The V0 will be sudden dipping will be there, and there will be extinction of the input. This current, when it will be zero, then this is beta, what we have discussed in half-wave rectifier also. So the current become zero in discontinuous current mode. In single phase half-wave rectifier, we have seen the importance of the capacitor filter. We will again discuss this in the full wave circuit. So here you have the RC combination now again as a part of a load, where capacitor act as the filter and R act as the load. So it produces an output voltage that is essentially DC. So whatever the output voltage here you are getting, it is much better format as pure DC, and ripples will not be present. And the analysis is similar whatever we have discussed for the half-wave rectifier with a capacitor filter. Here the capacitor discharge time is smaller than the half-wave circuit. So if you compare from the half-wave circuit to full-wave circuit, the capacitor discharge time is smaller due to the rectified sine wave in the second half of each period. So we have discussed this in the half-wave rectifier that after every 2 pi plus alpha term, the circuit will be energized again. So the capacitor discharge time is smaller. Output voltage ripple for the full wave rectifier is approximately half that of half wave rectifier. So ripple is also going to be half of the half wave rectifier. So full wave rectifier is better in this case because you don't have the ripple, which is again the half of the half wave rectifier. The peak output voltage is less in the full wave circuit due to the two diodes voltage drop rather than 1. So when we talk about the peak output voltage, it is also less in the full wave circuit because there are two diodes which drop will be taken consider, because at a time two diodes will be on. So you have to take the peak output voltage of both the diodes. So here you can see the waveform. This is similar to what we discussed in single phase rectifier. Only different in single phase half wave was that you have only one half to be rectified. Here both the half are rectified. So at certain theta, which is theta is greater than pi by 2, your current is becoming 0. And again at certain pi plus alpha, again the charging process take place. So output voltage is positive sine function when one of the diode pair is conducting, and the output voltage is decaying exponential. So you will be seeing that it is decaying exponentially rate, and you have the ripples which is delta of V naught. So this we will discuss what happened. So if we consider that the diode to be ideal, then the output voltage V naught, when one diode pair is on, then you have Vm sin omega t, and when the diode is off, this term is coming because of the capacitor. Now the diode become reverse bias at certain theta where the diode is off. That theta, this derivation we have already done in the single phase half wave rectifier, where we found that minus tan inverse of omega RC plus pi is the diode discontinuity period or the off period. And we have also seen that we need to find the slope, or the maximum output voltage and the minimum output voltage is determined by evaluating the V naught at the angle at which the second pair of diode will be on. So that is at pi plus alpha. So pi plus alpha, if you see there, the diode will be on here. So again this period the diode will be on. So at that boundary period we can equate the signal, and then we can find one expression in alpha, and these you have to solve numerically, because you cannot find the exact solution. You can find the solution using the numerical method at what alpha again the diode will be on. So the ripple delta V naught, which is basically the peak to peak voltage variation, is the difference between the maximum and the minimum voltage. So maximum voltage is Vm and the minimum voltage is Vm sin pi plus alpha. This will give Vm 1 minus sine of alpha. This derivation again we have done in half wave rectifier, which is similar. Alpha here, only thing is that it is larger for the full wave rectifier and the ripple is smaller for a given load. So your ripple will be smaller, which is good, and alpha is larger in case of full wave rectifier. And the peak to peak ripple voltage, if you see it, this derivation again we have done in half wave rectifier, which is Vm pi by omega RC, or we can see Vm by 2 pi RC. If you note this approximate peak to peak ripple voltage expression, then this is basically 1/2. So here two term is there, which is 1/2 of the half wave rectifier. In half wave rectifier you cannot find this two term, so that is double of the full wave rectifier. So these complete the total lecture on full wave rectifier, where we have discussed the different loading condition, that is R, RL and RLE, and we have also seen the importance of the capacitor filter in the circuit. So both single phase half wave rectifier and single phase full wave rectifier is complete by now. In the coming lecture we will see the importance of thyristors and their application in the rectifier as phase control rectifier. Thank you for